Hey, class. I just want to go through this real quick. Yesterday, I think, my video recording software did not complete the recording for the first part of the Glaciers lecture. So I'm going to try to go through this really quickly. I don't have a lot of time to do a full one, but I'd like to get something in. So if you like to watch these, and if you are, that you have something to go through. So we're going to go through glaciers today. Um, One of the things to know about glaciers is we have glacial evidence all over the United States. A couple of things they list here are the Great Lakes were created by the last glacial maximum. Alaska has a lot of glacier evidence. So does Yosemite Valley and Long Island. These are all places in the United States where you can find nice glacial features. Obviously, the fjords of Norway. Fjords are a integral part of glacial landscapes. The Alps, the mountain range in Europe, were formed by glaciers. So they do play an important role in both the hydrologic cycle, which is the water cycle, and the rock cycle. In the hydrologic cycle, precipitation can be trapped in glaciers for thousands of years. In the rock cycle, ice is an agent of mechanical weathering and erosion. So this is a nice picture of a glacier going down through a mountain valley. They mention here that glaciers are very thick, from hundreds of meters to thousands of meters, and it's a very thick mass of ice that originates by accumulation of snow and rain that freezes, gets compacted down from the weight of all the stuff that gets piled on top of it, and then recrystallization into ice. They move very slowly. Gravity is always pulling on them. So just like a river, glaciers are traveling down slope always. And they will travel down slope until they get to a level area or until they get to a area that is above the freezing point and they start to melt. There's two different main types of glaciers, valley glaciers or alpine glaciers. The valley glaciers slash alpine, those are kind of the same type of glacier, are relatively small. They move pretty slowly, and usually they're going down from a mountain range up in the high mountains down through the valleys. And so they'll show us a couple pictures of these in a second. The other type of glacier is an ice sheet. Ice sheets are found at the poles. They flow out in all directions from a center location. So if we're talking about Greenland or Antarctica, the snow and ice gets piled up on the continent, and the ice cap is really going to flow out in all directions. There's no one central direction that it ends up going. Um, they talk about ice sheets that happened during the last glacial maximum. They covered North America, Europe, and Siberia. They don't actually give us an image. Let me pull up one of those images real quick for you. So you can just go into Google and pull this up, open up a slide, and Google glacial maps and images. What's the one I looked at yesterday? Here we go. This one right here is actually a pretty good image. So this is from the last glacial maximum about 10 to 18,000 years ago. And you see all the glaciers coming down. These are actually the ones that carved out the depressions that are now the Great Lakes. You can see that the vast majority of Canada was covered up with ice, almost all of Canada. A good portion of the America Pacific or Atlantic Northeast, New England area, and central area here are all covered up with glaciers, as well as a decent portion of Alaska. All of Greenland is, and Greenland's over here attached to the top part of Canada. So since then, it has moved away. We'll talk about plate tectonics soon. But that's just a good illustration of the most recent glacial maximum, which was about 18,000 years ago. Ice sheets have advanced and retreated several times over the last 2.6 million years. And so it comes kind of in cycles. We get freezing, we get thawing, we get freezing and thawing. Note that the Arctic Ocean is covered by sea ice. So this is the Northern Ocean. Antarctica is a landmass and a continent, where the North Pole doesn't really have land on it. It's pretty much covered by sea ice, which floats on the water. Because it's floating on water and the water's not frozen, it can't build up a lot of thickness. So it's usually only a few centimeters to maybe 4 meters thick. It expands and contracts with the seasons. In summer, it melts and kind of breaks up and moves out, although the North Pole is pretty much always frozen. You get ice shelves that come out when your glacier reaches the edge of the land and goes out into the ocean, and they break off in an event called calving. They go through a couple of different types of glaciers. You have ice caps, which are smaller than your ice sheets or your ice fields. You also have Piedmont glaciers, which are glaciers that go down a valley, and at the point where the valley ends and they get to the bottom of the mountains, the glacier spreads out. We'll see a picture of that in a second. You also have some outlet glaciers that come out from your ice sheets. So here's a picture of Piedmont glaciers. Towards the bottom, you can see that it comes down through the valley and the mountains up here, and then it spreads out once it gets out of that valley. This is a big ice cap in Iceland, and you can see that some of these little protrusions coming out of the side would be little outlet glaciers that are kind of coming off from the main flow. Know that glaciers flow as a plastic, almost like a semi-molten plastic. So while they are hard ice, together as a whole, there's actually a lot of dynamics going on inside of it. It's not just one big solid chunk of ice flowing downhill. There's weak layers in between bonds. There's movement from side to side. The middle part of the glacier is moving faster. And you can have even rocks that are picked up by the glacier and moved up above the actual bottom level. Towards the bottom of a glacier, they have the upper 50 most meters is zone of fracture, which has a lot of crevasses. Crevasses are what you see here, giant cracks in the glacier that are actually pretty dangerous. If you fall in one, you're not likely to make it out. They go over glacial movement, how slow it is. Basically, 2 meters per year, less than 2 meters per year to greater than 800 meters per year, which is still not a long distance for an entire year. They also show that the flow is greatest at the center, so you have higher velocity in the center. What you can see here is a line of stakes that were put in 1874. By the time they came back in 1878, 4 years later, the middle stakes had moved much further than the outer stakes here. And so you can see the nice curved feature, and that continued through 1882, where the middle stakes had gone even further. So as the glacier moves down, the middle part is what moves the fastest. Today, we have better technology than just stakes. These are probably satellite photos that show your speed. Here's your speed bar down at the bottom, and also directional flow to show you which direction the ice is moving on the surface. So we're going to talk about glacial budgets now. Know that the glacial budget is just like your bank account budget. Your bank account total depends on how much you put in versus how much you take out. And so in a glacier, how much you put in is happening at the zone of accumulation. So how much snow and ice are you getting above the freezing line that actually gets incorporated into your glacier? Towards the bottom, how much you take out is called the zone of wastage. How much melting is there? What is your net loss to the glacier? In order to have a glacier, you want your glacier to have more stuff put in at the top than you have melting at the bottom. If you get that, your glacier will grow. It will advance down towards the bottom. If you're melting more than you're putting in, it will actually retreat and it will shrink and it will kind of back up the mountainside. Note that whether it's advancing or retreating, it's always headed down. It's always getting pulled down. The only thing that backs up is the actual end line here. So as it's melting, your snow is still coming down, your glacier is still moving down. It just looks like it's retreating backward because this end point moves further back up the mountain as it melts more. So here's your glacial budget. If you accumulate more ice and snow than you waste at the bottom that is melting out, you will have glacial advance. Your glacier will grow. If you accumulate the same amount as you waste at the bottom as is melted, you're stationary. You have a stationary terminus, and the terminus is the thing at the bottom here. I went the wrong way. The thing at the bottom here where your glacier terminates. And so if the amount you put in is the same as the amount that you melt, this will kind of stay the same. If you're putting in more than you're melting, it will move forward. If you're putting in less than you're melting, it will kind of move backward, all while the glacier is moving downhill. So if you put in less than you're wasting, you will have glacial retreat and your glacier will shrink. Even if the front is retreating, like I said, the ice is always flowing and moving downhill in the direction of the glacier movement. Here's an example of how sensitive glaciers are to temperature change. This is a glacier in 1941. Here's the same picture taken from the same hill. You can see the same hill right over here in 2004. Not only is the Muir Glacier completely gone, the Riggs Glacier is much, much smaller, and these hills now have vegetation on them, where before these are just rocky, desolate hills. So not a good sign for the environment around here and for that glacier. Now, what do glaciers do? How do they erode? They have a couple things that they do. First off, it's called plucking. This is when a glacier will lift rocks and giant boulders and blocks of rock up from the surface and kind of take them down with them as they move down the hillside. Another thing that glaciers do is abrasion. They will carry those rocks with them or push them along the bottom surface where they grind into other rocks. They scrape up other rocks. If they get scrapes in them, we call them glacial striations. If they grind up those other rocks, they're going to cause rock flour. So I will actually pull up a picture real quick again to show you some glacial striations. Glacial striations. And go to images, and you will see some really nice pictures of some good glacial striations. They're basically big scratches in the rock from the ice moving across it and from other rocks being kind of dragged across it. So there's some pretty good pictures here. This one's not bad. You can see the striations coming down. Let's look at another one. I saw that one the other day. This one's really good. So here's another image of your glacial striations where as the glacier moves, it leaves these deep cracks and gouges and grooves in the rock below. Let me check on my time. All right. So back to the PowerPoint. All right. We have a couple of other terms. First off, know that even if it starts off in a V-shaped valley, your glacial troughs will eventually turn it into U-shape. They're going to grind everything at the bottom of the V out and make it this nice U-shaped glacial trough. We have a couple other terms. Hanging valleys, when a smaller glacier leads into a large glacier, you get this kind of drop off because their bottom surfaces are not level. And so we'll see an example of a hanging valley in a second. Cirques and ariettes. Cirques are bowl-shaped depressions at the top of where a glacier forms. An ariette is a sharp ridge. A horn is the kind of the same thing, but instead of being a long ridge, it's just one very pyramid-like protrusion or peak. The Matterhorn is an example of a horn. And actually, let me go back to the very beginning. The Matterhorn, I think, is the cover of this book here. So here's the Matterhorn. This is a horn formed by a glacier, which is actually pretty nice. So fjords, also, that's kind of the most common term for glacial features. A fjord is a deep, steep-sided inlet of the sea that's been carved out by a glacier. So a big, long, deep lake that's kind of connected to the sea. So here's some examples of these. This is the pre-glacial landscape. Here's where the glaciers come in. You can see many different glaciers coming down and kind of forming into the main glacier. When they all melt away, you get these features. You have your cirques up top, these circular depressions at the beginning or the head of the glacier. We have a horn, a mountain peak that's been formed here, an ariette, a very sharp ridge that's been formed along here. And this is a hanging valley where this smaller glacier led into the main glacier, and it now has a drop-off that has a nice waterfall from the melted glacial water. If you can't see these too well on the video, the PowerPoint is obviously available on Canvas. So this is kind of where we're going to leave off for the next video, which I made today, and I'll put on Canvas along with this one. We're talking about deposits of glaciers and how they deposit their sediments. So glacial drift is pretty much any sediment of glacial origin that the glacier creates. Till is going to be material that gets deposited directly by the ice when it melts. And we'll see that till is actually what makes up the moraines. We'll see moraines 2 pages from now. This is a moraine, and they show you some different types of moraines. All the moraines are made up of till. And I think I'll go through that in the next video. Stratified drift is when you have a river or water that comes out from melted glaciers. Obviously, depending on the type of year, or not the type of year, the time of year, you will have more or less melt. So melt more in the summer, melt less in the winter. That's going to give your river different velocities, which is going to sort and kind of stratify the different sediments that get moved out of the glacier. And then you have glacial erratics, which again, I think I'll touch on in the next video. These are going to be giant boulders that get dropped in the middle of fields as the glacier melts and retreats. They got picked up and moved there, so they don't really look like they belong. There's no other rocks that really fit in with those glaciers or with those erratics, which is why they kind of call them erratic. It's not really what you think it should be. It defies logic. So I think I go over all this in the very next video, and this is where we left off. So I hope that helps you out a little bit, and at least I got some sort of video in, even though it's not the video I originally created. That one didn't really upload, so hopefully this one does. If you have any questions, please let me know. I would just like to remind you, and I'll try to send out an email in a second. We have some due dates coming up. The River Lab is going to be due at the end of this week, Friday, so you have 2 days left. Next week, next Friday, your Chapter 3 and 4 homework will be due. And we will have the Chapter 3 and 4 test. So I should send out an email pretty soon just to remind you about that. If you have any questions, please let me know, and have a nice day.